Today we're going to go over a guide on how to solve reversed fatigue problems. Now, the first thing for us to remember is what is reversed fatigue? It can be called completely reversed or fully reversed, but when we see this type of language, what does it mean? Generally, what it means is that the maximum stress during a fatigue cycle is of an equal magnitude to the minimum stress in that fatigue cycle, so that the magnitude of those two values are the same. If their magnitudes are the same and their signs are opposite, we have what is called a fully reversed condition, where we're going equal parts in tension and equal parts in compression. That results in a mean stress value equaling zero. So the average stress during the cycle is zero, and our stress ratio is equal to -1. This state of completely or fully reversed loading is the natural state of our stress life curve. This is from the Euler's rotating beam experiment. This is the type of fatigue that we would have, right? So if we've got this type of condition fully reversed, how do we then go about solving a fatigue problem? Let's start with our first step. The first step is for us to determine the rotating bending endurance limit, the S prime E, right? And this we can use our empirical rule for, where S prime E is equal to half of the tensile strength of our material if the tensile strength is less than 200 KSI or 1400 megapascal. And we set the SE prime to 100 KSI or 700 megapascal if the ultimate tensile strength is greater than 200 KSI or 1400 megapascal, right? So step one, get our unmodified endurance limit. Step two is to find the actual endurance limit of our specific part. And to do that, we apply our endurance limit modifiers, the Marin factors, right? Where we know this, we found the rotating beam endurance limit, and now we have to find each of these K factors and see how they apply to our specific problem. Things like size, loading condition, temperature, reliability factors, miscellaneous factors. We need to actually go through all of these steps for every problem and make sure that we either apply these factors if they are mentioned, and if a factor is not mentioned in the problem statement or it does not apply, we set that factor equal to 1, right? Now, for the Marin factors, they're detailed throughout the book, but there's actually kind of a cheat sheet or a crib sheet in section 619 that covers all of these within like a page or two. So if you want to be able to just apply them real quickly, you can go to that part of the book and it'll give you all of these factors in a really kind of shortened form, right? Once we've applied these factors to our unmodified endurance limit, we get the actual endurance limit of our part, right? All right, step three. If our part is notched, then we need to deal with the effect of that notch, how that notch affects its fatigue resistance. The first thing we would need to do is for our notch geometry, say we have this particular geometry, we'll need to find its static stress concentration factor KT by grabbing the chart from our appendix and then reading the chart to plot up and over for our specific combinations of dimensions in order to get that KT parameter, right? Once we've got the KT parameter, then we need to find the fatigue stress concentration factor, where KF, our fatigue factor, is equal to 1 plus the notch sensitivity factor times, in brackets, KT minus 1. Where that notch sensitivity, it comes from another series of charts. In section 610, there's two figures that have those Q charts. Alternatively, if we want to be super specific and have a repeatable answer, is instead of using the notch sensitivity factor Q, instead we can use Weber's constant, the characteristic length, the square root of A. If we use this form, with the square root of a, then we can directly use these polynomials for bending or axial loading or for torsion. And all we need is then the tensile strength of our material to calculate that characteristic length. And then we can put it together and get our fatigue stress concentration factor, right? Now we got this factor. What do we do with it? Well, the factor is applied to all of the stresses that are relative to the zero axis of fatigue. So this factor is our stresses are going to be multiplied by this factor for things like max stress, min stress, mean stress. And then we'll use those increased values of stress to calculate our cycles to failure, right? All right. Now the next step is to find Baskin's constant for our particular material, to find the A and B parameter. To do that, we need our endurance limit, the one that we found for our actual part, and we need our S1000 point, which is the fatigue strength at 1,000 cycles. S1000 is equal to a factor times the ultimate tensile strength. In our textbook, we're given that factor is a polynomial in terms of the ultimate tensile strength when our ultimate tensile strength is within a certain range. And if it's below a certain value, that factor is fixed to 0.9, right? So we'll just plug in the ultimate tensile strength, plug it in here as well, and we get our S1000. With that in hand, the solution to the A and B constants is in our textbook, where A is S1000 squared over the endurance limit, and B is negative 1/3 the log of S1000 over the endurance limit. So now it seems like we got almost all the things that we need. We've figured out our actual endurance limit. We've figured out how stress may be increased by the presence of a notch, right? A stress concentrator. And we found the material properties for Baskin's equations. Now, all we've got to do is start to try to solve our problem. In order to solve a problem, there's different ways we can go about it. The basics of Baskin's equation is that the stress amplitude is equal to the A constant times the cycles to the failure to the power B. So say we are given a cycles to failure. Say we know the cycles to failure. We desire that our part have at least 10,000 cycles to failure. What is the available stress amplitude for that desired cycles to failure? Well, we can put 10,000 in here, and calculate and find that fatigue strength or that stress amplitude below which or at which or below we have at least 10,000 cycles. But also we could have an issue where we have a design and we cannot have the stress amplitude exceed a certain number. The stress amplitude must be less than 50 KSI. How many cycles to failure would we have if it is 50 KSI or less? In that case, we can rearrange this equation in terms of the cycles to failure. And we can put in 50 KSI here, and then we can find how many cycles if 50 KSI was applied to our geometry, right? So we can, either search for cycles to failure or search for the stress amplitude for a given problem. Now, finally, there's one last thing we need to be concerned with, and that is how do we determine the effect of safety factors, right? So if determining finite life and we want to apply some safety factor to our design, then we can add that safety factor NF in the following form, where if say we're given a stress amplitude, but it needs a safety factor of 2, we need to add a safety factor of 2, then we'll simply put it in the denominator here, and that will knock down the number of cycles that we have available due to that additional safety within our design, right? So with that said, we've got the basis of how to solve fully reversed fatigue problem.